Then I think we can officially start. So it's my great pleasure to welcome you all to this webinar, to the RWTH AI Center Colloquium, which we are restarting today. Before I introduce our speaker today, I would like to briefly introduce Julia Mann to you. So Julia started actually this month as the new managing director in the RWTH AI Center. So Julia, do you want to briefly say hi to everyone?
Yeah, I think those who joined a tiny bit earlier heard me already talking. Welcome, everybody. I'm Julia Mann. I'm the new managing director of the AI Center. And I'm not going to take too much time because I know you're not here to listen to me. So I just wanted to let you know, if you're interested about any news about the AI Center future events, make sure you sign up to our newsletter or just follow us on LinkedIn, and we're going to put the links in the chat. And then without further ado, I let you, Sebastian, introduce our speaker of the day.
Yes, thanks a lot, Julia. And let's now move to the main person for today. So as you can see already, Philipp Hennig is with us, and it's my great pleasure to introduce Philipp to you. So Philipp holds the chair for methods of machine learning at the University of Tübingen. And actually, Philipp and I have known each other for quite a while. I think it's almost 10 years now. It was, I think, back then when I was a young postdoc starting at the Max Planck Institute in Tübingen, that literally my first week there was a summer school in machine learning, and I was fortunate to attend Philipp's tutorial on Gaussian processes. And then basically afterwards we started to collaborate, first master thesis, then joint supervision of PhD, and now, you know, GPs and Bayesian optimization and things are a big research topic also in my team. So that had some impact, but that's only kind of my personal story. Philipp is actually a very well-known researcher, lots of impact in the machine learning community. So Philipp has pretty much won all the basically young researcher awards that are out there. So starting with an Emmy Noether grant, which he then later exchanged for a Max Planck research group leader grant, to then also win an ERC grant. So pretty much all that you can have, basically he got, and he's also, together with some collaborators, coined the term of probabilistic numerics, where I believe Philipp has recently also published a book, which I know he has been working on for some years, I think it's fair to say. We are very happy to have you here today and to listen to your presentation. So Philipp, without further ado, thanks a lot for being with us today, and I give the virtual floor to you.
Thank you very much, Sebastian. In my defense, so yeah, I'm not sure how much you can see of my face at this point, but 10 years ago, I was also a young postdoc in Tübingen, so it's not like we're that far apart from each other. I was just happening to be organizing the machine learning summer school, so I got very lucky and got to squeeze myself onto the stage. I will admit that was 10 years ago. I was probably also already working on the book, so it really did take me a while to finish it. So I first of all should probably share my screen so that you actually see what I'm talking about. Otherwise, it's going to be a bit awkward. And secondly, I should say that, so I've been told that you're a relatively mixed audience. I'm kind of guessing that there are engineers in the audience and maybe computer scientists who are working on various topics, but maybe also including machine learning. So I will try to phrase what I'm going to be talking about in a relatively broad terms, but because I think that what I am talking about should be of interest to engineers, scientists, and computer scientists. If that doesn't quite work, then please do ask a question in the Q&A, and then I'll see it and try and answer. So the title of my talk is Probabilistic Simulation Methods in, and then everything, machine learning, science, technology. And I want to tell you what I want to, like, the setting I want to address in the setting of science, because it's maybe the one that links all of us together. So imagine it's, 1905. What does the scientific process work like at a point in time when people were thinking about the theory of science very sort of prominently? So here's a cartoon picture of the scientific process. Someone goes out into a field and they collect some data. So because it's 1905, they don't have a computer. They collect their data in a notebook, on a piece of paper. And then they go back to the lab, and then some humans get involved. A bunch of scientists sit down, they pour through the numbers, and they get some plotting paper, they draw some lines, and they reduce the data to some models of the world, some processes that describe the world. Typically, these processes are laws of nature. There's partial differential equations, like the Schrödinger equation, for example, or Maxwell's equations, and so on. Now, those equations you can then feed, not in 1905, but in 2015, into a big computer, and then that computer can simulate the world, both scientifically and also technologically. It can create theories for how the world works and how it would work if you change something. So in 2022, that's not actually how science works anymore, of course. Now data is much more prominent in the way we collect information. But actually, this is still the way that the algorithms work that do the scientific inference. So the numerical algorithms we use these days for simulation, they're actually inspired or invented, or they create functionality that was in fact invented sometimes 100 years ago. Here's an example of such an algorithm. Maybe it's the most textbook example of a simulation method, in this case for ordinary differential equations. Let me check that there's something in the chat that I can see this. Okay, thank you. So maybe some of you have seen this kind of algorithm before. If you don't know, then you don't have to understand what's going on. I'm just going to tell you this is a simulation method for solving ordinary differential equations. If you know, I can tell you this is a Runge-Kutta method. What I want you to understand about this code is 3 things about numerical algorithms that we use today. First of all, this stuff is old. So if you're a computer scientist, you may be able to recognize what kind of programming language this is. It's Fortran. And whenever something shows up in Fortran, that means it's probably been around for a while. The second thing to notice about these algorithms is that, so it's actually, you can also see that it's old from the comments in here. So this algorithm was implemented in 1996. It actually implements an algorithm that was invented sometime in the 70s by mathematicians in the US called Dormant and Prince. And in fact, it's actually an instance of a so-called Runge-Kutta method. These are algorithms that were invented in Germany in 1905. So that stuff is old. The second thing to notice is that these algorithms have a very rigorous interface. To call such a solver, you have to provide it with an initial value for this ordinary differential equation and a handle to the function that drives, the dynamics function, the vector field that drives the differential equation, and an integration range. But what's noticeably absent from this interface is a handle for data. There is no place here where you can push in some data. And the third thing to point out about this algorithm is that it's very rigid in its structure. Those of you who have taken a class on numerical analysis have probably learned about Runge-Kutta methods, and you've learned that they are defined by something called a Butcher tableau. In this case, this Butcher tableau is implemented here at the very end. It's a bunch of constants that you need to use. And if you've been to such a class, you've probably learned that you're not allowed to change those numbers, because if you change any of these numbers to a different value, the algorithm doesn't work anymore. That's a little bit awkward, because it means if we want to adapt this algorithm to a new setting, then it's hard to do that, because it's a very rigid structure. And this is interesting because these algorithms are actually still being used today in the most contemporary applications of numerical science. And that's because they actually solve a task that we still face. So contemporary machine learning algorithms are computer programs that adapt a model to data. That's kind of what you learn in the media, right? But actually what happens inside of a computer is the solution of a numerical computation. I don't have a slide for that. Maybe I should have had one. But so the algorithms at the heart of machine learning algorithms are basically the same that also run at the heart of scientific programming, computing, and maybe also methods in engineering. They are linear algebra methods, they are optimization methods, integration and sampling methods, and simulation methods, the one that I'm going to chiefly talk about today. So whenever people in a new field like machine learning, which is much younger, which was maybe sort of came of age in the early new millennium, encountered that they had these numerical problems to solve, they immediately discovered that there was already code for it. There were already algorithms around, like this wonderful old piece of Fortran code. And they actually work really well. So well, in fact, that it's very hard to build something that works better. Which makes sense because a lot of smart people have poured a lot of thought into these algorithms. So that means we now have this these algorithms available that save a lot of time because you can just call them, but they have this rigid structure. They are provided to us actually from people who lived generations ago. So now it feels like there's almost like a gap between the people who invented the algorithms and the people who use them now. So we really feel like we cannot touch those anymore. I think this is also maybe a new situation as sort of technology has aged, that we're kind of losing touch with the people who built the tools that we now use. And that's a bit awkward in the contemporary setting of data-centric science, you may call it, because we actually have new challenges which are not well addressed by these algorithms. And I'm going to show you one in a moment. But before I do that, I want to give you a brief idea of first a shameless plug, and then an idea of then I'll talk about my group. So the algorithms I'm going to be working, going to show you are a possible answer to these kind of challenges, and it arises from the idea then that we can think of what a numerical algorithm does actually itself as the action of a learning machine. So I'm going to show you more examples of this, but to give away the sort of the spoiler, any numerical algorithm estimates an unknown quantity that you cannot directly compute, like the solution of a differential equation, and it does that by collecting numbers that you can compute, evaluations of a vector field, of an integrand, of a loss function, and so on. So it estimates an unknown quantity from observable quantities, it estimates a latent quantity from data. It's an inference algorithm. It just so happens that for numerical algorithms, the data that they use doesn't come from the disk. They are not these numbers that are collected out in the field and then stored and then read in, like images for computer vision, for example, but they are numbers that are being created by the CPU or the GPU on the fly. But that doesn't really matter. They're just floating point numbers, and whether you read them from the disk or from the chip doesn't actually change much. From this point of view, one can build numerical algorithms that are explicitly phrased as inference engines. And these are called probabilistic numerical algorithms, and that's the book that Sebastian already mentioned, so I don't need to plug it any further. You can download a free PDF, by the way, if you like, from the link above. I should also say that everything I'm going to tell you about is the product of the work of my research group, these wonderful people that you see here, in particular of the people in my group who work on simulation methods. The group is sort of split up. The simulation experts are Marvin Pförtner, Emilia Magnani, Jonathan Schmidt, Nathanael Bosch, Philipp Tonarp, and Nico Krämer, who I'm going to talk about later. And the other people work on other kind of problems in machine learning. So why do we need new simulation methods, actually? So to explain this, I'm going to give you a very simple example that's hopefully nevertheless interesting. So here is a data set that probably everyone can recognize. So these are counts of infection rates in Germany during the first 1.5 years of the pandemic. At this point, we've all been looking at these data sets for long enough so that people are kind of, now we can even look at them again, but there was a phase when people didn't want to look at them because they were kind of stressful. You will remember that around the time this kind of data set was collected, the main question, maybe the most urgent question to society was, how does this time series continue on the right? So what is the next thing that's going to happen? Are numbers going to rise again? How far are they going to rise? Should we have another lockdown? So this here clearly is, it's an extrapolation problem, right? There is a time series here. It's a bunch of dots. It's even a univariate time series problem in this very simple view that we're looking at here. So if you are a sort of, I don't know, first maybe you're, if you are my straw man, which is like a first year master student in computer science learning about machine learning, then your knee-jerk reaction might be, oh, I've got tools for this in the machine learning toolbox. Neural networks, Gaussian process regressors, whatever your favorite tool is, maybe something you've learned from Professor Strimpe and Leibe in their respective lectures that I guess they're teaching this term. So if you throw a standard neural network at this problem, let's say a ReLU feed-forward perceptron, it's going to extrapolate like this, which is useless, right? And this is actually not at 0 as it happens. It's actually a straight line because it's a property of neural networks that they extrapolate linearly. But you can use anything else you like, a Gaussian process regressor, some other nonlinearity in your neural network. They're going to extrapolate in a different way, but it's always going to be boring. Maybe they'll extrapolate linearly upwards or exponentially, or they'll go back to 0 or whatever, depending on what your model is. None of these are actually useful. So to make a meaningful prediction, we need to encode some causal structure, if you like, but maybe a better word actually is a mechanistic structure. We need to understand what's actually happening underneath this data set. And a way to encode this is mechanistic knowledge, or maybe a law of nature, but here it's law of nature sounds like a big physics insight, right? But it's a differential equation. And for pandemics, there's a very simple ordinary differential equation, this one. It's called an SIR model. I'm guessing that many of you here in the call have heard about those before. What I'm showing you here is the most basic form of these SIR models. It's a three-dimensional system, and it works in the following way. We take the population and we separate it into 3 groups. Everyone is either susceptible, so they haven't had the virus yet, or you are infected, or you are recovered, SIR. So if you are susceptible, then you can infect yourself by interacting with an infected person. So if there are a lot of infected people around, a lot of people get infected, and then they move from the susceptible group into the infected group. P, by the way, is the size of the population. It's just a constant. So this term shows up here with a plus, so people move from this group to that group. And then once you are infected, you can recover with a certain rate. So a certain proportion of the infected people at every time step recovers, and then they move into the recovered group. And in this very simple model, the idea is then you're safe, you're never going to be infected again. Of course, the situation would be more complicated, and you can imagine that the actual predictions that we saw around that time in 2021 used a more elaborate model. But at the very heart, they were actually they basically had this structure. They were a bit more high dimensional. So this is the kind of differential equation, an ordinary differential equation, that we can solve with this kind of algorithm. That's actually what this algorithm is made for. You give it a 3-dimensional vector, a handle to this function, and then off it goes. It's just a teeny tiny problem, which is that this equation contains a bunch of constants, beta and gamma. We don't know what those are. So you could pick some value. I picked some, and then I fed it to this algorithm because I need to know what beta and gamma is, because there's no way to tell the algorithm that I don't know, right? If you do that, you get a simulation that looks like this. This is equally useless as the original machine learning method did, right? It just moves up and then comes back down again. Now, if you see that you're tempted to move around beta and gamma, I've actually done this a little bit. This is like the best fit I could get. You always get a hump. Maybe if you've studied this kind of models before, you know that you'll always get a hump that comes back down again, and that's it. You'll never get 2 or 3 humps like this. So what we have here is a situation where the algorithm requires us to provide something that we don't actually have, the values for beta and gamma. And it can't deal with something that we actually do have that would be informative about these things, which is these red dots, the data. There's no way to put these red dots into this ODE solver that I just showed you. Now, so part of the problem is that I've oversimplified what's going on. I've assumed that beta and gamma are constants. They should, of course, not be constants. They should be time varying. So they should be what's called a latent force, if you like. There's a latent process that moves up and down. And of course, in fact, that's actually what happened, right? So beta is called the contact rate. It's how often people meet with each other. And everyone remembers in early 2020, what we all did was not meet each other anymore. So the contact rate went down, and that's why this curve didn't actually explode like this. It came back down again. And then we got a little bit carried away, and we got in contact again, and we got this whole business that everyone remembers of. So we will need to assume that beta is a thing that changes through time. It's actually a function. But we still don't know what it is. Actually, this just makes the situation even harder. We really don't know what to do, right? There's now this non-parametric object, a function, which we would like to figure out from the data, but the algorithm that we use to do this doesn't provide us with a way to do that. Now, actually, of course, it's 2022, and people are smart, and they have come up with ways of solving this problem. And that those ways involve, let me show you a slide on this, involve starting with an initial guess for what beta might be. So you parameterize this latent force, beta, in a bunch of parameters. For example, it could be a neural network itself, could be the output of a neural network, or the output of a Gaussian process, or some other kind of model. And then you start with an initial guess for what beta was. You feed this to the ODE solver. Then the ODE solver produces one of these lines, like this red line I just showed you. And now you want to compute a gradient of this loss function, or loss function could be the log likelihood of the data, right? So how far is this thin sort of fading red line from the from the data? That's some kind of residual. You'd like to compute a gradient between of this residual with respect to the shape of this function beta, and then follow that gradient. Use your favorite optimizer, which these days I guess is Adam or something. So there's just two tiny problems of this. The first one isn't actually much of a problem. It's that this code is Fortran code from the 1980s or 90s, yeah? And therefore it's not differentiable. It's not it doesn't have automatic differentiation. But no problem. Thank God for Google. People have already implemented this for us. So here is the exact same algorithm implemented in JAX, maybe the most contemporary of deep learning libraries built by Google. What's maybe sort of important to point out, I hope that you can read this. If you can't read it, then say something in the chat. So I can also zoom in a bit more. So this is in JAX experimental ODE.py. And here's the algorithm again. And you can just check again, right? So here is the Dorman Prince method. That's the exact same as before, right? And it is now implemented in Python, or actually in JAX, because it's more modern. But it still has this property that we encountered before. So in particular, let me see if I can find the right code. It still contains those magic numbers. Here they are again. You can actually check. The first one is 1/5, and the first one in the Fortran code is also 1/5. It's a good sign that we're on the right track. And it also still has this interface. Let me just see if I can find the right interface, that you have to provide a handle to the function, to the initial value, and to the time that you want to integrate in. And then it does something fancy inside. It actually calls a function called _ODE_in. So underscore means you're not allowed to touch it from the outside. Where is that thing? It should be somewhere, probably have to go up. Here it is. And then it does something that allows us to actually compute the, am I in the right thing? Here we go. That allows us to compute a gradient because it's automatically differentiable. But so what we can now do is we can follow this gradient and optimize, right? And this approach is called, this approach is called simulation-based inference or approximate Bayesian computation, or you can use it to implement a neural ODE. And there are various other kind of algorithms that use this idea that you basically use the old code and wrap yourself around it. So that's essentially what's happening here is we're building a for loop that optimizes our samples around a closed box that retains the structure that mathematicians invented in 1905. The problem with this is that this algorithm implemented in Python here actually contains itself a for loop. So you don't really see this in JAX because it's hidden in this scan function here. But what this algorithm does is it repeatedly evaluates this dynamics function f, this ODE that I showed you on the previous slide, over and over and over again. And then once it has done that, it returns a solution. And then we get to change that function and start this process of over and over and over again. And every computer scientist knows that nested for loops are a dangerous thing because they may hide the inefficiency. So let's think about what an ODE solver actually does. ODE solvers, here's a cartoon picture of what an ODE solver does, exactly this method I just showed you. It solves problems like this. So here is an ordinary differential equation. It's an implicit statement about a curve x, which says that the derivative of this curve in the parameter time is given by the value of a nonlinear function f evaluated at the value of this curve. So that's why it's an implicit statement. We don't know what x is, so we can't really solve this in closed form. We also know that the curve goes to some initial point, x0, at time 0. So the situation is a bit like this. Here is a very, very simple ordinary differential equation. This f, this vector field, are those arrows in the background. The solution to the problem is this black curve, which we assume we don't know yet. That's what the algorithm is supposed to tell us. And we know that this curve starts at some point. It's an initial value problem, like the one that we're trying to solve at the moment. So we have this little dot here. So now what solvers for ordinary differential equation initial value problems actually do is well, it's this complicated mathematical process encoded in this Fortran code, but you can also think about it as the collection of information. We know that the curve goes through this point because that's the initial value. So we can use that to evaluate this function f at this point. And that will give us a first data point produced by the computer, this arrow, which tells us that the curve continues to the right like this for a while at least, because we assume it's locally smooth. And that means we can extrapolate forward a little bit in time and make a guess for what the curve might be at this point in time. And that we can collect more data and evaluate the vector field at that point, get another observation and use that to refine our estimate of the solution of the problem. And we can keep doing this forward through time. And once we arrive at the end, we have an estimate, this red curve, for what the actual curve, the black curve, may be. Now, you can already see that that's a regression problem, an iterative, recursive regression problem where the algorithm chooses the points where it wants to evaluate. It's actually an active learning algorithm, essentially, that estimates the solution by collecting its own data. And I've already phrased it like this as well. What you see here is the output of a Gaussian process regression algorithm, a very specific one that can be implemented very efficiently, a Gauss-Markov process, that produces this estimate with uncertainty. I've also drawn a bunch of samples. And what I can tell you is that this way of building a numerical algorithm actually is first very close to the classic algorithm. It's very close to what this Runge-Kutta method does that I've just shown you. It's not the same thing, but it's structurally very similar. And it actually inherits the good properties of these classic algorithms. Those good properties are, A, that if you increase the computational resources of this tool, so if you allow it to take smaller steps, then the red line, the thick red line, the estimate, converges to the black line at a high polynomial rate. So that means if you increase the budget by a factor of 2, the error drops by a factor of 2 to the q, where q is some number larger than 1. It's for the classic methods, it's 4 and 5. That's why this thing is called Domen-Prince pair 4 and 5. It's actually possible to build these algorithms such that they reach orders 11 on sufficiently smooth problems. Secondly, and that's a new property, these algorithms, these algorithms are as expensive as the classic methods. They have the same computational complexity. And thirdly, they have a new thing, which is this distance between the thin line and the thick line. So that's an error estimate, an error bar. And it's possible to show that this error bar contracts at a rate that is a worst case bound for the distance between the black line and the red line. So it's a meaningful error estimate, if you like. These algorithms are now available as a piece of code, and there's a really nice thing about them. They are Gaussian process regressors in Gauss-Markov states, and that means they can be implemented as Kalman filters. And now I hope that the engineers have woken up, because that's of course a tool that you're all familiar with. What if I told you that you can build simulation methods as Kalman filters? So you can think of a simulation method as actually like an empty spine that starts out. That's this red thing in the middle. That's a Markov chain of states that describe the dynamics of your system. In our case of this COVID example, big X would be S, I, and R. And then various derivatives of S, I, and R. So the first derivative, the second derivative, the third derivative in time. And they are linked to each other by an LTI system. And that means if we have observations of this LTI system, we can condition on it by using various forms of Kalman filters and smoothers. Not just the basic one, but also the extended Kalman filter and various other features, like all the other variants of Kalman filters. So in particular, we can condition, and that's the new thing, that's how these solvers work, we can condition this Markov chain on what we call information operators. That's like a module that you can plug into the ODE solver that says at various points in time, the difference between the first derivative of this curve and some nonlinear function evaluated at the 0th derivative of this curve is equal to 0. Now, if f were a linear function, we could do this in closed form. But f is not a linear function, so we need to linearize it. We need to do a Taylor expansion. But you know, it's 2022. We've got automatic differentiation. It's not a problem. We can do that, use the extended Kalman filter, get an approximate Gaussian posterior for x from those observations. But we can do something else as well. We can, in the same process, as we go through time from the start to the end, hook in other observations. other types of observation operators, information operators. For example, we can tell the solver that we have evaluated the state of the system at various points. We've measured I, for example, and just condition on this observation. So if we would know what the ODE was, we wouldn't necessarily actually need this data. Well, assuming we know all the boundary or initial values as well. But there are things in our problem that we don't know, and that's this latent force beta. So what we can do is we can just take that latent force and plug it into the state space. So we basically expand the state space of this Kalman filter and just say there's, in addition to S, I, and R and all this time derivative, there's something else called beta. And we have a model for beta as well. It also changes like an LTI system, actually like a nonlinear transformation of an LTI system through time. Now please, if I tell you that this here holds and this function also depends on beta, figure out how the two relate to each other. When we do that, we get a prediction like this. So here is an algorithm that solves the ODE forward through time, extrapolates into the future, and at the very same time also estimates the contract rate beta. And it does that in a single solve of the ODE. So it starts from the initial value, it goes through it once, and then it's done. The cost of running this algorithm is comparable to running this classic piece of Fortran code exactly once, not many times over. And as you can see, it returns a richer form of output. It doesn't just estimate the this latent force beta, it actually estimates it with uncertainty. It returns a transformed, non-linearly transformed Gaussian process estimate from which we can draw samples. And those of you who use Kalman filters a lot know that drawing from the posterior is possible at essentially no cost overhead. So we have to go through the data once and then pass back with a Kalman smoother, which is more or less for free, and you get a dense output from which you can sample. And what you can see is that there's interesting structure in this prediction. So early on in the pandemic, when the infection counts were nearly zero, there is high uncertainty in the contract rate beta. By the way, beta is bounded between 0 and 1. That's why you see this nonlinear transformation of this Gaussian process. So there's high uncertainty. Why? Well, because we don't get data about what beta is. If you remember, I'll go back to this ODE for a moment. Sorry, I have to jump through my slides. Here it is. So beta only shows up in a product of S and I. So if I is 0, there's no way to figure out what beta is. There's no information gathered about beta from observing I is equal to 0. Because any value for beta would give us the same observation. But then as, there we go. Now, as the infection counts increase, we learn something about beta. It has to go down because otherwise this would have been an, at least initially, exponential curve going up. And we all remember that we had to flatten the curve. Because the curve got flatter, that means the contact rate has had to come down. We become more confident about the algorithm, about the contact rate beta. And then you may remember that in the summer of 2020, if you were in Germany in the summer of 2020, you may remember that that was the first summer of the pandemic, and in Germany at least, the case rates actually went right down. And people got, we actually went on vacation during that summer because there were so little cases. Now, during that phase, again, the number of observations was very low, and that means we learn very little about the contact rate. There are not many infected people in the population that can act as probes, basically, to tell us what's going on. And then the second wave hit, and the third one, and we become more confident again about what beta was, and then later on, of course, so actually, this is a bad plot. The data ends here, and then the rest is a test set. So we actually become uncertain again because we predict into the future. Now, of course, if you know something about what's going to happen here, if that latent force isn't actually latent, but you control it because you can, reinstate lockdowns, for example, then of course you could use that to try out different scenarios. You could turn it into a control problem from a latent force inference problem. So these algorithms now actually exist. My group and I have spent the last 10 years or so, since this machine learning summer school pretty much, building code to make these algorithms work well. Initially, it was a big philosophical question. We tried to understand how the classic methods work and how to improve on them. And the first time we implemented these algorithms, they were super, super slow. They weren't really useful for anyone at all. The first time I implemented them, they were simple Gaussian process regressors, and that meant they were cubically expensive in a number of time steps, and it was all totally silly. Now, thanks to some very smart PhD students, like the aforementioned people I've shown you on the slide, these algorithms are actually have actually become very fast. So here's a recent plot from the PhD thesis of Nico Krämer, showing that's essentially a work precision diagram. So at the bottom is the error that the algorithm makes, and at the y-axis is the runtime. And what you can see here is a current implementation of one of these ODE solvers I just showed you before Nico improved the code. That's sort of the early thing. Here is SciPy. So if you've used a SciPy ODE solver before, then that would be this code. This down here is this JAX solver. So this green line here is this code, exactly this code. So this nice parallel automatically differentiable, beautiful piece of code from Google. And this blue line is now Nico's code after he re-implemented it properly in JAX. So you can see that this algorithm is now basically as fast as this other piece of code. It's very close to each other. There's tiny differences in optimizing the code, but there's not really a point anymore, because if you look at the gap to SciPy, you can kind of imagine what's actually going on. So I'm showing you this because I want you to actually try it out. I want to convince you that this is not the level anymore where we are playing around with simple kind of tools that shouldn't actually be used in practice. But in fact, we've reached a point where these algorithms are now so sophisticated that they can actually be used in scientific applications. There's three different kinds of code libraries to sample from. We have a didactic piece of code, which we call ProbNum, where you get modular, relatively high-level implementations of these algorithms. They're not particularly fast then, because they're very flexible and they're largely written in basic Python, NumPy. And then there are these two fast implementations by the two senior simulation PhD students in my group, Nico Krämer's code in JAX and Nathaniel Bosch's code in Julia, if you are a Julia person. So if you want to try out these methods, please go out and try them. They are simulation methods that allow you to use various different kinds of information in simulation in a modular fashion. Someone asks, are there PyTorch implementations? Not that I know of, but that's something we need to work on. If you'd like to, please look at the JAX code. You can transform it if you want to. I just said these tools allow you to plug in these different modules, right? So two modules I've already showed you. One is the differential equation itself. So you can tell the algorithm that there is a law, an underlying differential equation that controls the dynamics of the system. And you can condition on that. The second one was what you could call, so this kind of knowledge about the physics driving the system, you could call that a mechanistic knowledge or physical information. There's this word now shows up a lot in machine learning, right? There's this physics informed, mechanistic inference, that's this kind of information that I'm talking about. The second kind of information is what is the good old data, which you could call empirical information, so knowledge from the real world. But you can condition on various other kinds of information. For example, and there's a plot that Nathaniel built with this fast Julia code I just showed you, where you condition on conserved quantities. So that's slightly different from a differential equation. If you like, it's a symmetry. So here on the left, there is this is a Henon-Heile system. For those in the know, this is an orbit of a system in a gravitational setup. And it's solved to a very high precision with a high precision solver with high computational budget. So you can see that it's a nice, smooth, looks like a ball of wool. In the middle, you can see the same system being solved with one of our probabilistic solvers at very low precision. So it has a bigger step size and therefore it makes more error. And you can see that it loses this nice structure. It doesn't kind of go back to the points it started on, and instead kind of gets a little bit out of whack. But this system is a physical system for which we don't just know the laws of nature driving it, we also know some conserved quantities. We know that there is a Hamiltonian, a function defining the total energy of the system, which is conserved through time. So there is another nonlinear function of the state whose time derivative is 0. So we can plug that in as well into this algorithm. And then if you do that, you get this plot here on the right, even if you use the same step size as for the solver in the middle. So having additional information about your system, like for example, that it conserves energy, as defined by some Hamiltonian, can be included as well. Now, of course, there are classic numerical solvers that are have this property as well. They're either called geometric integration methods or symplectic solvers. So algorithms that, solvers that are aware of a certain Hamiltonian and make sure that it's conserved. But this modularity is really the strength of this approach, that you can plug in different forms of information, and in particular also can live with the fact that the information may not be complete, because Kalman filters can deal with observation operators that are not fully informative about the latent state. You can also condition on various other kind of information. So in Nathaniel's paper, which was recently published, he shows some other examples. For example, he also, if you know some algebraic information about your differential equation, like for example that it is second order, that actually provides information. You might be surprised about that if you're a numerical mathematician, because you may have learned that all ordinary differential equations can be represented as first order ordinary differential equations. That's almost true, but not quite. There is some information getting lost when you do that, and you can provide it to the solver, and then it runs better. You can also encode differential algebraic equations. So these are more general implicit functions that just say something about the state is true at every point in time, and so on and so on. So I actually would, I could show you more, but I won't, because I hope that we might have some questions, even though this is this virtual setup. So instead, I'm going to wrap up and tell you what I've tried to convince you of, and then maybe we can have a bit of a conversation. So the main message I wanted to get across is that, first of all computation is actually inference. Everything a computer does with floating point numbers is to collect information about some quantity that you can't directly compute. Of course, if you can directly compute it, that's also just collecting information. It's just a boring form of collecting information where you don't need to do any inference. If you think about computation as collecting information, about collecting data from the chip, if you like, then it makes sense to use the same mathematical language to encode the process of learning from data from the disk and of learning from data from the chip. Because then you can combine them flexibly together, like in the example I've shown you, where we combined mechanistic knowledge from the differential equation with empirical knowledge from data being collected out in the real world, in the physical system. And of course, and I haven't shown you examples of that, but you could also condition on further kind of what you might call vague expert intuition. You know that the curve has to have certain shapes and scales and so on, and include those as well. When you think about it this way, then numerical algorithms are learning machines. And that means if you are a person who builds learning machines or builds signal processing algorithms, then you are qualified to build your own simulation methods. These tools of yours, it's actually like for mechanical engineers, I guess, right? So if you're a mechanical engineer and you're building a big machine, you're typically using a small machine to do so, right? A lathe or an electrical drill are also machines. And good engineers know about the machines that they use to build bigger machines. So people who build simulation, who use simulation methods, should also know about the internals of those simulation methods, because they're also just machines. And one way to think about them is from the probabilistic perspective. One advantage of that, of building a probabilistic numerical algorithm rather than a point estimation numerical algorithm or a frequentist numerical algorithm, is that they return uncertainty quantification along the way. And the nice thing is that this uncertainty quantification can actually be done in closed form. It doesn't necessarily add cost overhead, because, you know, if you've built a Kalman filter, you know that computing the uncertainty quantification around the Kalman filter doesn't necessarily add cost over just producing the point estimates, because you require the matrices needed to do the point estimation already. The matrices you need to compute the point estimate are also used to construct the uncertainty estimate. If you'd like to know more about these algorithms, you can find more in the textbook that I've already mentioned, which is available as a free PDF from this website that you see here. Of course, you can also buy it in every good bookstore. And you can check out our software libraries, both the didactic code at probnum.org and the fast algorithms in Tornadocs, that's Nico Kramer's library, or Nathaniel Bosch's Julia implementation. And we're currently teaching a course on probabilistic numerical algorithms, because these algorithms go way further than simulation methods. You can also apply this idea to linear algebra, to optimization, and to integration. It's going to be a few more months until you'll see the first of those on YouTube. But if you're interested in these methods, then please check out our YouTube channel, where you can already find some research presentations, and there'll be a proper course sometime soon. Thank you very much.
Thank you very much, Philipp. So I guess you can't hear the others clapping now. That's the downside of the virtual seminar. So thanks a lot for this great talk.